Good afternoon to those of you who just arrived, and welcome back to those of you who were here before. Let's see, we're going to launch into the second half of the Convergence Conference, and we're going to start with by hearing from a team that brings together some very interesting disciplines across the campus. And in particular, what's very rewarding to me is it brings together physicists and engineers. You think that that would be a common occurrence. But this team has really taken ideas from nanophotonics and technology and food security and brought those together to try to solve some really difficult problems about how do we detect efficiently and effectively pathogens in all kinds of threat environments. So with that, I'm going to introduce Professor Chen, who is a professor of physics, as well as a professor of electrical and computer engineering, and the newly minted director of the newly announced this afternoon Purdue Quantum Science and Engineering Institute. Yong, congratulations and welcome.
Thank you very much. Okay. Thank you so much, Thomas, for the kind introduction and support. And it's a great pleasure to be here. I really appreciate this opportunity and this program. Actually, I also really like the lighting in this room, right? Wonderful setting to start a talk on photonics, right? Okay, yeah. And lighting and logo also remind me of a dreamland, almost, yeah? And the Big Idea program is a program that brings people from different disciplines with different research strengths together to make big dreams and to take the important first steps to realize some of these dreams for the global impact. So I will tell you 3 stories in this talk, okay, on how we work together and also with the various departments and centers, including newly established ones, that in our program represent 3 examples, example of interdisciplinary research. But let me introduce quickly, important, our fellow dreamers and actors at teams. As Thomas pointed out, brought physicists and engineers together. You may think, well, they work all the time together, right? But what kind of engineers, right? So usually, as much as I want you to pay attention to the names of colleagues, but even more so, the department affiliation. How often do you see physicists, photonic engineers, work with agricultural engineers? I mean, they have tremendous expertise in these different domains, but traditionally, they don't work so often together. But when they do, like in this program, really amazing new technology start to be developed, which is the example I give you in a few minutes, okay? That actually impact our everyday life, we think. But let me start with make observation back to photonics. So I'll tell 3 stories, a past story, a current story, and some future stories. So of course, this is a start with photonics. Let me first point out, make the observation that, of course, we use photonics very often in our everyday life. My laser pointer is a photonics device, right? There's lightings. Your cell phone has a lot of photonics elements in it. But most time we use photonics to put on a show, right? Displays. We rarely, at least directly, utilize a tremendous measurement and detection capability of photonics. And yet, photonics is the most sensitive measurement detection method known to man, okay? And that's what excites me as a physicist and excites a lot of engineers, and want to make good use of this. There's no better example to actually give example using LIGO, which many of you know is a gigantic laser interferometer that is so sensitive that can detect the tiny ripples emitted by the space-time ripples due to black holes coming from lots of light years away and long, long ago in the past that cause the displacement of these giant mirrors at length scale smaller than the size of an atom. Yet, that can be detected by LIGO. That's how photonics, or even quantum photonics, can be sensitive. As exciting as it is, I personally actually have not worked on this giant photon device like LIGO, but I work on something much smaller. So a couple years ago, actually almost 10 years ago, I and then Purdue nuclear engineer colleague actually worked on a program, actual programs supported by Department of Homeland Security as well as DoD Defense Threat Reduction Agency on developing nanotechnology or nanomaterial-based sensors, such as based on graphene, a wonderful material with lots of amazing properties for radiation detection. Okay. This is actually motivated by an issue that has actually been talked about for years. For example, Oppenheimer the scientific leader and one of the father of the Manhattan Project, pointed out in 50s that actually biggest danger, he says, not from atomic bombs, but actually from the suitcases brought into Manhattan, potentially. People can smuggling in suitcases through borders, these nuclear material, people can make dirty bombs, so on and so forth. And a little more recently, the issue was also brought up by former President Obama. Actually, this was before he became president. Actually, he spoke right here in Purdue in this conference. He actually pointed out this issue too. Says nuclear terrorism is, on the long term, a very grave threat. Okay, so there's a great need to detect these kind of develop this kind of technology, new generation sensitive detectors of radiation. Okay, actually, how about $1 billion supporting, magic invisible wall of monitoring detectors, right? So that's kind of is one of my personal, entry point of looking at photonics, and we actually developed one of the earliest graphene-based devices, photon to electron conversion, transduction device that not only convert one photon into one electron, but control lots of electrons. That's a new generation sensitive photonic detector that can actually detect signals, including optic signal from some of these radioactive materials. And also, later on, we start collaborating with other colleagues like Shalev and Sasha and the teams, other kinds of graphene plasmonic, again, very sensitive photo to electron conversion device in graphene and other interesting materials. So, most of us perhaps we had a lot of fun working with photonics, okay? Although most of us maybe on the everyday basis, we don't worry so much about nuclear terrorism. But everybody, okay, unfortunately, if you don't like it, but almost everybody will experience some episode of food poisoning, or multiple ones in your life. I had one just about a year before we started Big Idea Program on the flight from Caribbean. Not pleasant, had a big impression on me. But this is very common, and it's a healthcare societal challenge, but it's also a scientific and technology challenge. On the very general level, it is actually very challenging to detect small quantity of pathogens. Could be foodborne pathogens, and when they're pathogenic, they are live cells in a large volume of some background. For example, some water-based volume could be your food, water, or could be tissue or blood. So this is not just an important problem for food safety, but also for healthcare, cancer detection, and so on and so forth. Okay. So this is kind of start of my second and current story. Okay. So there are two sides of this story. So you'll see how agriculture engineer working with physicists for engineer actually may start to making difference and some interesting new development for this need. So one side of the story, right, coming from my distinct colleague, Mike Ladish and his team in agriculture engineering, traditional way to detect bacteria, right, is to culture them, grow them in your petri dish, and just wait, for a day, when they grow enough, make the colonies, you start to detect, right, using whatever method you have. And Mike's team developed this new paradigm, new technology, actually before we started the Big Idea program already, and they, instead of doing this growing, culture of bacteria, not that, but instead of send the samples with the current, these bacteria, pathogens, through very powerful microfiltration setup and technology. Actually, part of that use hollow optic fiber, interesting use of the fibers. And then you get this very concentrated paste-like sample with a very concentrated bacteria, for example. Then you can detect much more efficiently with, instead of days, maybe just a few hours. Then, and start showing my card, our card, concentrate, amplify, recover, detect. Then you can interface next, so he's receiving photonic technologies, allow them to quickly detect this concentrated bacteria, for example. Okay, so there's a picture of this filtration setup. So let me tell you the second side of the story, which from the photonic side. But before that, let me reflect a little bit, say, what do we mean by detect a live bacteria? We talk about detecting live stuff, which is not just a static image of a dead cell, but you're detecting life, detecting functions, okay? And life rests in motion. In fact, I learned from my biology colleagues, even in cell, there are a rich variety of the dynamics, motion occurring in broad range of length scales, time scales that capture the dynamic fingerprint of the life and function of cell, like a bacteria, okay? If you can take a movie of this, in principle, you really know what you're looking at, whether you're looking at cancer cell, a bacteria cell, and whether they are harmful or not. So we need a very sensitive motion detector working in the broad range of time and length scale. And one of the most powerful motion detectors is based on this optical effect Doppler effect. Many of us are very familiar with Doppler effect. The policeman holding device measuring car speed based on Doppler effect. The babies in the womb being measured by ultrasound, and the health, the blood flow based on Doppler effect. And there are many, many applications. And here's where my colleague in physics department, David Notti, his team comes in. For many, many years, they've developed a Doppler-based spectroscopy that is a very, very sensitive way. Actually, it also uses laser interferometry, the kind of basic physics underlying LIGO, but in a different way. They're very sensitive to take movies, how cells and tissues move. So these are pictures of a cancer tissue. And actually, they were able to do this very quickly, looking at almost a tomography, different layers of these tissues, how they move. Some of that is dead, without actually having to go through a time-consuming process and cut them in slides. This is, again, a wonderful technology enabled by photonics. You might say, well, so both studying these cancer tissues, studying bacteria, they are all kind of biology, right? They should be worked together. Not quite, not often. The field, scientific, has become so specialized. Most of us become experts. Even within the life science and biology, I've heard, if you go to NIH study group, every special kind of disease has an institute, has a study group. Actually, very, very rarely, people who study cancer cells work together with people who study bacterial cells like E. coli. That actually is very rare. But that did happen in our program. So this is an example. I won't go into technical detail. When Dave, for example, applied this very sensitive motion detector, which usually he applied to study cancer cells, now including some of these bacterial cells from Mike, for example. These are some of the first images, movies, dynamic spectrum, fingerprints of how bacteria, like E. coli and other pathogens, infect tissues in real time. This kind of movie has never been taken before, and this is truly a really, really exciting and paradigm-opening new science and new technology that is developed. So we're very excited about this work being enabled, and thanks again to Discovery Park, this kind of new paradigms. So this is an example of convergent new exciting research that I want to tell the current story. Okay? And along this program, there are other examples I want to go into, but physicists like myself and my colleague, for example, Vlad Lab, that usually measure nanomaterials of solid-state materials. We also learn how to measure optical spectrum, image on individual cells. These are actually pretty well developed measurements, but it's still kind of exciting for physicists to do this, and then we start thinking about other interesting ideas. For example, my colleague Sasha Potaseva has had a nice vision, say, well, let's take example of very, very common biophoton device that everybody, I'm sure, you have been exposed to when you have a health checkup. This black pulse oximeter, which measures kind of oxygen content in your blood, is actually a mini spectroscopy kind of a simple device. And this is very successful. It's very useful, and it's simple and cheap, but very useful. And also, our most common kind of photonic include device, cell phone, smartwatch. You take pictures, selfies. A lot of us take pictures of food and put it in your Instagram or whatever. And then, maybe, just in future, this is one dream, right? In future, these kind of personalized photon device, not take images, just the image. You can take spectrum of your food. You know the nutritional content. You know whether it contains pathogen or not, whether it potentially will go bad. So this line of development will open a new era of personalized, miniaturized biomedical photonics. So let me end my talk by something even more futuristic, okay? Which you just heard today. Today is a good day, a quantum leap. So a lot of physicists, Feynman, Steve Chu, I heard them say, biology is next frontier of physics. But another side is physics is always next frontier of biology. Think about amazing measurement technology developed by physicists. And the biggest frontier in physics is quantum today. And today you just heard the launch of a new era of quantum research with you. Let me give you an example. I'm also very happy this program allowed us to kind of start involve some of the young and new faculty we hired. For example, my colleague, Tong Tang Li, a very creative young faculty we hired in the last few years. You've seen his picture, ultra-fast spinning nanoparticles, but he also wrote a very visionary article a couple years ago to say, if you can embed a spin, okay, into a bacteria, for example, some biological system, then you can actually prepare an entangled state involving, say, a bacteria. This actually got a lot of press. People started drawing very Star Trek-like images, which is very thought-provoking, which I'm sure will generate a lot of interesting discussion and research to come. For example, fairly recently, we had a meeting also involving some other colleagues, physics and agriculture engineering, biology engineers, started talking about questions such as, what is the minimum energy? It's hard to talk about life without talking about death, right? You need to kill one cell, for example. Actually, I'm somewhat proud that I don't know much biology, but I did collaborate with one of my colleagues in the team, Yong, essentially take the silverworm cocoon and turn it into some kind of photoelectric photodetector device. But then the upshot is that actually you can shine light. They are photoelectric process in some of these biological samples. You can generate charged particles like radicals actually end up kill the bacteria. Okay, so actually this work from Yong actually clarify some of the mysterious mechanism how some of the silkworm cocoon actually seem to be a naturally wonderful disinfectant or something. But the bottom line is now we start thinking about design experiments, optical based, even quantum optical based, that can start actually asking question, can we actually have a quantum, start doing quantum measurement, or this is getting in the very future land, start asking the quantum between life and death. This is you can dream tonight. So with that, this is the end of my talk. So I really hope I give you 3 stories, past, current, and some futuristic, that demonstrate when you bring people from very different disciplines together in a program like Discovery Park, Big Idea Challenge, really things we didn't even know about a year ago actually happened, which I hope will really be some example of really new paradigm technology that's born here at the Purdue in Discovery Park. Thank you very much.
Terrific. About 2 years ago or so, I read a report from the National Academies that was called Convergence and the Future of the Life Sciences. An entire report that was written by very eminent people from around the country. It was around this convergence of physics, engineering, and the life sciences. And to see these kinds of progress and these kinds of activities going on, these kinds of convergence happening here on the campus of Purdue is really, really terrific. A lot of potential for this. So questions for Yong? So I have a question for you, Yong. Detecting pathogens, or radiation has been a challenge for decades, right? And actually commercializing devices that actually can be used by first responders, by Homeland Security people, and so on, is actually quite hard. Where do you see the path from what you're doing now going forward into the future, and sort of working with some of those agencies, in the future to sort of actually get some of these ideas into the hands of the people who go out there in the field and try to protect our food supply, our ports, and everything else?
Yeah, definitely. So you raise a very good point, right? So it is very important, and some of the ways we're trying to help the line exactly is to work with stakeholders actually in the field, with food-related supply companies, and also companies developing devices, but also FDA. I think Mike's team, he has a lot of connections and ongoing work with some of these industries as well as government agencies to actually speed up the process, actually making deployable devices. And even, last fall we had a workshop, and we planned another workshop bringing some of these stakeholders to work together. I think it's important for not just within university. That's the whole idea, the point of the Big Idea program, we have to engage with these other outside entities. Yeah, very important point.
Good. Yes, please, over there.
Thank you very much. I was curious, the recalls with romaine lettuce. I know sometimes when something like that happens, they pull all romaine lettuce off the shelves because they can't pinpoint sometimes exactly where it comes from. So would this provide an opportunity where in the store they would be able to scan those that produce there and determine whether it needs to be pulled off the shelves?
That's a very good question and great vision. I would hope indeed in future, just like people in nuclear engineering talk about nuclear forensics, I think Thomas knows field very well. In future, when you have this sensitive enough device, you can actually talk about these pathogenic forensics. Okay, my bio colleague can add me on that, but I think that's a great question and vision.
I think ideally you would also want to be able to detect the E. coli infestation, in the produce before it gets to the market.
Right.
I think that's really what you're after, right, Mike?
Yeah. Please.
It's been my pleasure to really interact with the physicists such as Yong and my colleagues, Sasha Boltaseva, Lad Shalov, David Nolte, Young Kim, etc. But I think the key concept that is so revolutionary that Yong has presented is we're using living cells to detect pathogens no matter what they are. And one of the issues with romaine lettuce is until they found out what caused it, they didn't know. And actually the detector was an organism, a person. So what is happening here is by combining, well, I hate to be.
Right.
So what's happening here is combining the developments, the really interesting developments of detection and quantification of cancer cells, David Nolte, with the spectroscopy that Yong has developed, and the nanophotonics from Lad and Sasha, is the fact that if we take a cell, even if we don't know what it is or what sort of pathogen it is, we can detect a very big change in the fingerprint of the metabolism of that cancer cell. So what we're doing is actually using a living cell as a sentinel for pathogen detection. And doing something like this, and Mohit's shaking his head too, he worked in George Whiteside's lab, so he knows a lot about this. So doing something like this not only has applications in the food store, but also for defense. Because often a warfighter will be exposed to something and you really don't know what it is, and you want to know, is it bad? And so again, with these technologies which can be miniaturized, and that's Sasha's vision, in fact, they may be a little bit expensive for a grocery shop, or there what you try to do is catch it before it gets to the store, okay? But for certain applications, it would work well.
Yeah, thank you very much. It's been great.
Hello, I'm Mariela Fernandez, and I'm a new grad student. I'm from the Department of Botany and Plant Pathology. So I think that this, I think that this kind of new technology will help us to try to work with the field, do some pathogen detection in the field, so that will help us like to try to detect and try to make some management. So my question is, do you think that that will help like in the field? Like how we can approach this new technology to the field, to the crop itself?
I think thank you. That relates to the first question that we discussed. I think we like to see that impact all the way to the field and working with companies and agencies. Also with a program such as, you may know Birck has a very large Wabash, wind project that's deploying sensors in the farm, agriculture with farmers. And we talk about embedding some of these sensors in these deployable large network sensor. Then there's a big data aspect also involved. I think this is actually indeed a very exciting approach. And some of my other colleagues can comment, and we can talk about some of that in the panel too.
So if I could add to that, in fact, what the Department of Horticulture is doing, I think of Lori Hoagland as well, is they've discovered that plant biofilms, which are naturally occurring, sequester in very low concentrations pathogens, which generate these biofilms so that they evade detection. These biofilms then are transmitted through the food we eat. In fact, are now known to be vectors for human pathogens. And so the question is, can these methodologies be used to quickly detect this? And the answer is yes. And that's one of the objectives we have in developing this from the foods sorts of applications. So that was really a very perceptive question. Maybe you work with Professor Hoagland, or?
Yeah, well, I'm a new grad student, so I'm just starting. My approach is like use some new technology, some sensors for trying to detect and differentiate some diseases in wheat. So maybe we can talk later.
I think Mike wants you to go to graduate school, and he's going to hire you. Any other questions? Victor.
Thank you. John, wonderful presentation. Just a brief story that hopefully will help me to pose my question. Many, many years ago, a U.S. missionary in the mountains of Peru told me a story that he presented to a local native people with a small solar cell in the early 60s to explain we're storing force from the sun to make work our radio receiver here. And the community leader asked, wow, that's fascinating. How is this little mechanism affecting the sun? Was the question of the native people. So my question related to that would be, is there conversation about secondary effects that this photonic technology at this micro level in cells will have? I don't know if that's part of the conversation. Thank you.
Thank you for your question. I think yes. I mean, we do. When we bring people working with the cells, with a physicist, photonics experts together. I mean, in the general context, it's a light-matter interaction, right? So very much, the more we understand how photons interact with cells, the molecule in the cell, this process, then the more ideas we can actually generate to have a new kind of sensors, or not just sensors. This actually is an active device, which you can actually, so we call this a little bit photodynamic, you can actually do something to the cell. It's actually going to the domain, even treatment or disinfection. So I think understand on the micro, even nano level, the light magnetic interaction in biology system is an area with huge potential that really connects to so many fields. Yeah. In fact, even just a couple of days ago, we were talking to a new, I think we have an incoming director for Bingley, that he also has some idea, would like to organize a new workshop later in this fall on this topic. Thank you very much.
Thanks very much, John. Terrific.
Okay. Thank you.
Thank you.